This video is going to talk about thermodynamic cycles. So far, I've identified different types of processes whereby a gas is heated or cooled, or work is done on it, or the gas does work itself. All of these are processes in which one of the state variables is constant, okay? Or the situation with an adiabatic process where there is no exchange of thermal energy. So here we're going to look at cycles, which are when we start putting these processes one after another, okay? And what we end up with is sending a gas through different states, and we return it eventually to its initial state through whatever processes. Now, I noticed from the last video, some of you guys disliked my last two videos. I get a feeling like that's probably because of the amount of stuff you had to write, or maybe because it was, confusing what was going on in terms of the writing, or what I'm saying, and trying to keep up with both. So here is a suggested strategy, okay? First of all, actually the first suggested strategy is to figure it out on your own. The second one, if you can't figure it out on your own, is what I'm going to tell you. What you should have done is pause it, write everything that's on the screen, fill in whatever's there, okay, and then go and follow what I say, or listen to what I say, then pause it and write it down. But come up with a way, all right, you can do it, where you listen to what I say, and then pause it and look for what I've written that matches that. And I'm trying to go along on the screen too, going top down through the screen, explaining what's happening, okay? So I've given you the definition of a thermodynamic cycle, all right? We're going to look at this cycle here, the very first example. We're going from point A to point B to C, D, and back to A, all right? Just a few things I want to review before we jump into this. The first is our ideal gas equation, okay, which is PV equals nRT. With this equation, all right, if we consider two different states, and I've already done this derivation right here, okay, if we consider two different states, and we end up with this P1, we can combine those, okay, since we can basically show that PV over NT is equal to R for any state, okay, we can set those PV over NT equal to each other. And if we say N1 and N2 are equal to each other, if we have a closed system, we have this combined ideal gas equation, which we can use to compare the various states of the gas as it goes through a cycle like this one, as we're going between all these different stages, okay? So this is a very useful equation right here, all right? So the very first thing that we should be doing, right, with this is looking at cycle A, process A to B, okay? So process AB is going to be isochoric heating. And how do I know that? Well, the change in volume is equal to 0. That tells me why it's isochoric. And if I look at it, okay, the pressure is going up, and that must be going from a lower to a higher isotherm in order to do that. So we must be adding thermal energy in order for that pressure to go up. So we can calculate that change in thermal energy. Again, this is another equation that I've already derived. And you can go back in the videos, or back in the notes, or even check the textbook for the derivation of this equation, which I highly recommend, just taking the time to do that, okay? But the change in internal energy, we know, is equal to 3/2 times the change of the product of the pressure and the volume. So if we look at that, on the page there, okay, just above the chart, it tells you what the initial values of the pressure and volume are, okay? And we can substitute those values in, and what we end up with is an increase to 600 joules of internal energy. So if we come back, actually, excuse me, yes, that's right. Okay, so if we come back here, okay, we go look at cycle AB, we have these three columns, delta Q, delta U, and W, okay? We look at all three of those columns. All three of those are going to have to follow the first law of thermodynamics. In other words, all three of these, delta U, the change in internal energy has to be equal to the thermal energy added minus the work done by the system. So it's isochoric, there's no expansion. That means no work has been done. We go back to that really quickly, okay? Delta V is equal to 0, and work is equal to pressure times change in volume. I'm not sure if I've shown you where this equation comes from, but I would be more than happy to do that for you in another video, actually. And actually, no, you know what? I can probably do that right now. So actually, really quickly, if we look at, we have some piston cylinder assembly, okay, and this is some height h, right? And the piston is some surface area A, okay, and the molecules inside, they're bouncing around every which way, right? And if what we end up having happen is that piston rises, okay, so we have a new H over here, so we'll call this H1, this is H2, and we still have this area over here, okay? The work that will have been done is going to be equal to the force times displacement, all right? And if we consider the force to be equal to pressure inside the gas times the area over which that's exerted, which is the area of the cylinder, okay? We can plug that in here. And the delta S over which this happens, okay, is going to be the change in height, so change in height. And really, if we look at A times delta H, this is just equal to the change in volume. So what we end up with here is that work is equal to pressure times change in volume, okay? I think I might have shown that to you as well, just deriving it from the definition that we had for the integral of a PV diagram. Anyways, so we take that value that we had before for 600 joules, all right? That's our internal energy. That's what we're going to place here, our change in internal energy into the table. And then because the work is equal to 0, if we use our first law equation, we end up with delta Q being equal to positive 600 joules as well. So in order for this isochoric heating to occur, we need to add 600 joules of energy, all right? So that's a pretty basic one for the first process. The next process, okay, is going to be from B to C. And when we look at B to C, okay, whoops, sorry. It's all the way back here. Yep, it's at the bottom here. So from B to C, we actually have isobaric expansion. All right, we have a change in volume, an increase in volume at a constant pressure. And when we look at that, we end up with 1,200 joules of work being done. Well, if we calculate the difference between both of these states for the internal energy, which is just going to be delta U is equal to 3/2 times the change in the product of the pressure and the volume, we end up with a change in internal energy based on the two different states being equal to positive 1,800 joules. So if we plug both of those into our first law, we see that the amount of thermal energy that needs to be added in that entire time, in other words, the gas does work, the internal energy of the system goes up by a certain amount, we need to add 3,000 joules of heat, all right, in order for us to be able to do that work and for the internal energy to go up based on how it changes between those two states, okay? So now we're at C, so we're going to go from C to D, okay? And from C to D, again, this is another isochoric process, so there's no work being done. All right, so work is equal to 0 joules, all right, because the delta V is equal to 0. And if we look at the change in internal energy, we get negative 1,800 joules. And since the change in internal energy must equal the change in thermal energy, we must remove 1,800 joules in this process to drop the pressure down from C to D, okay? And the reason why that value is higher than A to B is because it's happening at a greater volume, okay? So we need to remove more thermal energy, all right, for that change in pressure to happen. Okay, so the final process here is from D back to A. This is what defines the thermodynamic cycle, is that we end up back at our initial state. So from D to A, if we look at the work that we do, we're at P naught times delta V, we end up doing negative 400 joules worth of work. And that negative 400 comes from that negative delta V. And if we do a similar calculation, all right, with delta U equals 3/2 delta PV, we end up with a change of internal energy being equal to negative 600 joules. So if we plug those into our first law, we end up with a heating requirement, a cooling requirement of negative 1,000 joules. Okay, so this is going to be our isobaric compression, and in order for that to happen, work is being done on the system, and the change in internal energy is negative 600 joules. So therefore, the amount of heat removed must be equal to negative 1,000 joules. And if we consider the entire system for the whole cycle, we add up each of these columns, and we see the total amount of thermal energy added needs to be 800 joules. The total work that we've done is 800 joules, and that makes perfect sense. If we end up back in the same state, the total change of internal energy better be 0 joules, since we start and end in the same state. And anything we put in, we must get out Here we're of course assuming that these are all reversible processes, which is not possible, but that we're not losing any heat to the surroundings, and that that's why the total thermal energy we put in is equal to the work done by the gas, 800 joules, and those balance out. Okay, and that's it for our thermodynamic system, and that's pretty much. Here we go. What thermodynamics is. Okay, so all right, a little bit of state variable review here. Okay, using the ideal gas law, we can calculate the temperatures of each of the states. So you can get the temperature at state A. All right, just going to be P naught times V naught divided by NR. At state B, okay, if we use the values that we have there, it's 3 P naught times V naught, and when we look at that equation, that's just 3 times the temperature at A. At the temperature at C, we're at 3 times the original pressure and 3 times the original volume, so it's 9 times the temperature at A. And finally, for state D, it's 3 times the temperature at A. Okay, so we're just looking at these processes. Okay, the properties of each of the individual thermodynamic processes. A to B again is isochoric heating. Temperature goes up, internal energy goes up, work equals 0. Delta Q is positive. Isobaric expansion, work done is positive by the gas. Internal energy goes up and the temperature goes up, so therefore delta Q must be positive to keep up with all that. All right, the isochoric cooling, all right, there the temperature is going to go down because we're cooling it, okay, and we're moving thermal energy. No work done here, okay, no compression or expansion, and so the internal energy there is going to be equal, the change in internal energy is going to be a decrease, okay, negative delta U. And then finally from D to A we have an isobaric compression, and so we have negative work being done since it's negative delta V. We see a negative change in internal energy or decrease in internal energy because of the decrease in temperature, and for all that to happen we must cool it in that entire process for that internal energy to decrease while work is being done on the gas, that work being put into the system there. Okay. Now I've drawn this here with some arrows going into each of these points, into each of these lines, telling us that in each of these processes here, thermal energy is being put in. All right. For process A, B, and B, C, it's being taken out for C, D, and DA, and work is being done by the gas in BC and done on the gas in DA. When we look at the PV diagram, okay, if we look at just B from B to C, we can get a certain amount of work done here, okay? And if we look at just D to A, we can look at the work that's done there, okay? So what we see is that we have this work, positive work done on the gas, positive work done by the gas, this negative work done on the gas, and the difference of those two is the total work being done in the entire thermodynamic cycle. So you can see how we're subtracting this rectangle from this bigger rectangle right here. And it's all about finding the area under the curve when we're looking at a PV diagram for the work that we're trying to find done by the cycle. Okay? So the properties of the entire cycle, the gas will return to the same state that it was originally in, same pressure, volume, temperature. The delta T needs to be 0, so the change in internal energy has to be 0, and this is only true for ideal gases. Since the change in thermal energy, internal energy is 0, the thermal energy transfer, heat transfer, is equal to the work done by the cycle. The work done by the cycle is the area enclosed in the PV diagram. This is a big one. You will be asked to find this. Okay? If the work is positive, okay, then delta Q needs to be positive. We need more heat we need heat to be put into the system so that it can be removed to do work. And so that's just conservation of energy, first law of thermodynamics. All right? So that's going to do it for our first video. This is our introduction to thermodynamic cycles.